It should be ardently noted by any serious student of mathematics and geometry that the golden ratio of phi and the Fibonacci sequence and its resultant approximations of phi are not exactly identical number sums. If we were to take, say, the golden ratio, being here expressed as n minus m over m equals m over n, and construct from it a golden rectangle that, by fractal division, may be interiorly reduced down ad infinitum, and likewise may expand beyond its depicted borders following the same pattern, we would find this shape differs only very slightly from the same pattern formed by area squares determined by the Fibonacci sequence, but that a difference, however slight, does nonetheless exist. Therefore, even though to ancient reckoning such distinctions may not have mattered, in modern times we may realize the Fibonacci spiral and the golden ratio spiral are very, very much alike, but that they are not exactly identical. The difference between the golden ratio, phi, spiral, and what later came to be called the Fibonacci sequence, spiral, however indiscernibly minute, nevertheless fascinated ancient Pythagoreans, who included the natural shape of the nautilus shell spiral as well. Again, while none of these are a mathematically exact, identical match for any others, to the ancient mind such apparent discrepancies were trivialities besides the practical use and workability of such findings. If, indeed, they knew in antiquity that a golden ratio spiral existed separately and apart from what would ultimately be called the Fibonacci sequence spiral, it remains too difficult to ascertain at present if they applied this difference into any meaningful work. In short, it appears now that, to the ancient geometers, for all intents and purposes, the golden ratio spiral and the Fibonacci sequence spiral were one and the same thing, and, if not exactly mathematically identical, close enough to be considered the same essential premise and concept. Clearly the golden ratio was known to Pythagoreans, who used the pentagram as the chief symbol for their school and later underground cults. The golden ratio occurs twice inside a pentagram. Once as the ratio of one leg of one stellation to the length of one side of the interior pentagon, and once as the ratio of these distances combined to the distance from one stellation along the interior pentagon to the next. It was highly likely these early pre-Christian Pythagoreans that began the affiliation of differing models with the pentagram's orientation, pointing one tip up and two tips down, or else two tips up and one tip down. While the early Pythagoreans likely considered the obverse or upright pentagram lucky and symbolic of even numbers and clockwise rotation, and the reverse or inverted pentagram unlucky and symbolic of odd numbers and counterclockwise rotation, it is unlikely they associated the former with the microprosopis of Adam Cadmon, nor the latter with the goat of Mendes, yet by then. The only angles present in the pentagram are those of the interior pentagon, each being 108 degrees. The angles of the stellation tips, each of these being 36 degrees, and the angles between the stellations and the interior pentagon, and each of these is 54 degrees. If we examine one of the pentagram's stellations by itself, we see that it contains innately angles of 36 and 54 degrees, and the golden ratio, which may be in turn expressed simply by the measures 2 for each side of the interior pentagon and 3 for each leg of each stellation. This demonstrates succinctly that a ratio of 1 to 2/3 is also a simple and not entirely inaccurate approximation for phi that was undoubtedly known of and probably also used in the arts and architecture by the earliest human civilizations. In examining the example of phi, or the golden ratio, in the specimen of the 1 to 2/3 proportion, the parts of these 36 and 54 degree angles in the pentagram have very important roles to play. Let us first consider the model depicted here, which shows at its base a line segment labeled AB that is divided at C between the blue line AC measuring 3 and the green line CB measuring 2. Now we simply square these sums by raising them in exponent. The line of 2 we make one side of a square with all legs of length 2, and thus with a total area of 4. The line of 3 next to it we make a square of 3 by 3, thus with a total area of 9. Then we simply repeat the ratio present on the base line in each new square's sides, such that above the square of 2 by 2 equals 4 is another square of 3 by 3 equals 9, and above the lower square of 3 by 3 there is another square of 2 by 2 equals 4. So, as you can see in the diagram, the upper and lower 3 by 3 equals 9 squares overlap one another in the central 1 by 1 basic unit square. This central base 1 unit square, shown in red, may be, in turn, seen as occupying a space between 36 and 54 degrees from any corner, with its central diagonals of 45 degrees also aligning along those of the greater square formed of all these smaller pieces. Such a larger square formed of smaller pieces may be called a geometric gnomon, as in its sense as a plane figure formed by removing a similar parallelogram from a corner of a larger parallelogram, or, more generally, a figure that, added to a given figure, makes a larger figure of the same shape. The gnomon of the preceding base 5 or area 25 square represents only one such corner of a parallelogram, and as we see here, there are also larger and smaller gnomons flanking it along the diagonal as well. The first gnomon we find measures a golden ratio between 1 and the square root of 2. The second between 2 and the square root of 8. The third between 3 and the square root of 16. The fourth between 4 and the square root of 32. And the fifth between 5 and the square root of 50. In this diagram, we may see also that beginning with this third iteration, there is overlap with the fourth, and between the fourth and fifth, there is overlap as well. As we shall see next, this pattern continues on for the known remainder of larger sums in this sequence. When we consider a base 1 unit square and render a gnomon from it by use of a semicircular arc connecting one corner to its opposite and dividing the diagonal into a length of 1 and a length of square root of 2 minus 1, we establish the basis for what is, demonstrably, a formula applicable across this whole pattern, that being that n times the square root of 2 minus n will always equal the diagonal of the square gnomon formed in the corner of a larger parallelogram with sides equal to n. This postulate holds true for square root of 8 minus 2, square root of 18 minus 3, square root of 32 minus 4, square root of 50 minus 5, and so on. It can be demonstrated, given the space in which to do so, that this pattern extends into infinity, and that this postulate applies all across this pattern from its least to its greatest extensions. Here is a slightly more detailed mnemonic progression chart showing iterations for squares between 1 times 1 equals 1 squared and 14 by 14 equals 196 total unit squares in area. Here we may somewhat more clearly see how these mnemonic subsquares form in each corner of a parallelogram, so divided, such that for each size scale square, the smaller corner gnomon remains the same proportions and occupies the same percentage space. The smaller corner gnomons all expand between the angles of 36 and 54 along the 45-degree diagonal, and they all follow the axiom for their diagonal lengths that n times the square root of 2 minus n, where n equals the length of any one side. Thus, this makes the distance of the mnemonic diagonal easily calculable even for a square of area 196, where it is the square root of 392 minus 14. To perform the process of squaring the circle according to ancient reckoning, handed down to us in modern times as sacred geometry, it was necessary to have studied all these prerequisite concepts, and, as we shall see in the next section, the process of squaring the circle can be done by anyone, but will have little meaning if one does not also know and understand all these concepts as well. Thus, we shall see how we must combine the concepts of pi, phi, the golden ratio, the Fibonacci sequence, the square root of 2, as well as mnemonic, expansion-contraction patterns, in order to square the circle.